However, what is important is that clustering analysis, autocorrelation analysis, actually gives us information about the scatter too. Because as you can see, in that case also the clustering signal is reduced. And we think actually that we need fairly low amount of scatter in order to fit the data. Now there's a complication here that I think will haunt us in the long term in terms of clusters, which is that it's actually hard to find how to determine whether a given cluster is a cluster or just a satellite in a larger cluster, or maybe just something just outside on the outskirts of a larger cluster. And so we have tried to deal with this by removing all the close pair clusters in the max BCG. In fact, we find that it's about 5% of the max BCG clusters are for sure not real clusters because they are too close to the larger cluster. We cannot reproduce the clustering correlation function if we don't remove close pairs. All right, but here actually I'm showing you that removal of close pairs, which is remove everything within two times the visual radius, and we get this kind of result. In fact, here I'm showing you the result with 3 times the visual radius, and basically, so forget about this. This is nothing. I mean, there's no signal here, but here you can see, we kind of reproduce well the clustering correlation, but again, high values of scatter are not favored. One thing that has nothing to do with lensing, but is actually very, I think, important, is that clustering amplitude at 2 times 10⁻⁵ happens to be in cosmology independent. It just happens that at that place, b squared times b times sigma 8 is independent cosmology. And that's because, at high masses, the bias actually decreases more rapidly than sigma 8. At low masses, the bias is essentially constant, independent of sigma 8. And so this transition, which happens to be right at the 10 to the 14 solar masses, where the clustering amplitude is independent of cosmology. So that's actually a useful factor, because it means that this result is actually essentially independent of cosmology. And that's what we use. All right, and so basically, again, in these terms of analysis, sigma 8 of 0.8 gives the result which looks like this. If you add a realistic amount of scatter, which would be something between here and here, you see we're slightly below the data, and so we need slightly higher sigma 8. But the errors are getting, the important thing is when you do this full analysis across a whole range of scales, you cannot use these scales, because here we have baryonic effects which enhance the signal and stuff like that. All right, but if you everything above 1 megaparsecs, you can see basically that the errors, when we do this kind of analysis, the errors are much smaller than what I was doing before, where I was just feeding NFW profile out to wherever we can trust NFW profile, which is to 3 megaparsecs. Here we do basically the whole fit to the n-body simulation, and we get much smaller errors because we can use a whole range of scales. So we haven't finished this analysis yet, so again the answer will be something like 0.8 something. Okay, let me talk about gravity modifications and what we can study using this cross-correlation techniques. There was a session yesterday, I gather, so let me not go through these details of these alternative models. Some representative models I'll talk about are f of r and Mond, relativity generator Mond called Teves. So first I want to mention something which we've recently done in the data, but the statistic has been proposed by Zhang et al. A new cosmological test, which is where you take 2 different large-scale structure tracers and you try to compare one to the other. And the reason you want to do this is because so far all the probes have been either based on classical tests, redshift distance relation, or something based on the amplitude of clustering. CMB has amplitude. Large-scale structure has amplitude. There's always amplitude in there, right? So if you could do a test which is based on clustering, but where amplitude cancels out, then that would be, qualitatively new way of testing the testing that is actually, as it happens, to be very sensitive to these modifications of gravity. Okay, so one way to do this is to take this particular combination where you take this cross correlation between lensing and dark matter, the other correlation of the galaxies. So that's the 2 probes that I mentioned before. Before I was squaring this one and divide by this one to cancel the bias, but now I'm going to cancel the bias by bringing in the 3rd observable, which is the redshift space distortions. Redshift space distortions are sensitive to this parameter beta, which is b over this logarithmic growth rate f. And so in this particular combination, again, bias cancels, but not only bias cancels, the amplitude fluctuation sigma 8 also cancels. And one is left actually with something which is just dynamical without the amplitude fluctuations. In this case, omega matter, for standard models, omega matter over the logarithmic growth rate f. So we've tried this on the data. Again, same data as I was showing you before, LRG data. And we have used the redshift space distortion parameter beta measured previously by Tegmark et al. And what we find is this result, that this EG thing, I've measured the redshift roughly 0.2, is about 0.4, which is in perfect agreement with lambda CDM model, which is shown here. So these are data points, these are average over whole data points, this square. Now FFR is 1 sigma away from the best fit model. Not yet statistically significant, but you can see that if we improve this method by a factor of 2 or 3, we'll be able to put some strong constraints in these models. And this TEVES, which is this model which tries to get rid of the dark matter, this model is ruled out more like 2.5 to 3 sigma, and so it's definitely appears to be inconsistent with the data. And the reason for that is that this model actually needs to have a rapid growth of structure at low redshifts, and that basically increases this logarithmic growth rate f and makes this quantity EG small in that model. Okay, so this is again qualitatively different information where we are combining lensing information with the clustering information. In this case, clustering not just the 2-point correlation function, but also redshift space distortions. Second thing that we're looking at in terms of modified gravity modifications, we're looking at the profiles of the clusters just outside the virial radius. It turns out that inside the virial radius, there's this thing called chameleon effect in modified gravity models that basically makes things not different from GR. Outside also it's not so easy to distinguish things from GR, but in this transition region there is something that one can look for, and in fact one sees an enhancement in intensity profile. Right? So we look for that in the data. In fact, you can see there are two, there's some hint, in some cases there's a double peak, so that's, these are simulations from Schmidt et al. That he just ran, and so this is where we are right now. So there's a hint of a double peak. So we tried both a single peak and a double peak, and this is comparison to the data. The bottom line is there's no evidence, although in this case actually there's almost 2 sigma evidence, but nothing statistically significant. But one can put constraints on the modified gravity, and of course, as we improve the data on the dark matter profiles in the other parts of the clusters, we can do this better. All right, what about the inner profiles, where we fit to the NFW profile with various concentration parameters, which enhance the signal relative to the virial radius in the inner parts, and that's how we can try and fit for the concentration. We have done this over a whole range of masses, from the Milky Way types of halos to, for example, LRGs, which are in 3 times 10^13 solar mass halos, and then to these clusters that I've just shown you before, right? And then there's also a very nice analysis by Subaru, cluster analysis, which also they fit data, stack data, and they find concentration parameters. The bottom line, I think, is that these are our average. This is the Subaru data, and this is the lambda CDM model. If anything, the concentration is slightly lower, but nothing that I personally worry about. It's between 2 sigma or something like that. There's no evidence for enhancement of concentration as predicted by some hydrodynamic simulations, which usually have overcooling problem. That's why they enhance the dark matter profiles in the inner parts too much. When you actually do it realistically, realistic simulations actually don't actually show much effect. In fact, some simulations do show the opposite effect. That actually, when you have a lot of AGN feedback, you have just the opposite. So the bottom line, I think, as far as we can tell, lensing says that there's a reasonably good agreement in terms of dark matter halo profiles in the inner parts compared to the predictions. You can see also the lensing, the predictions are that concentration should be higher at low mass than at high mass, and there's some evidence for that. Basically, that the concentrations are higher at low mass than at high mass, but the errors are still large. I want to talk about something that is more for the future, but it's an idea that actually goes to Uli Penn, which is how can we now, now that I told you that it's a good idea to combine clustering and lensing, well, how can we combine it and learn even more? And the idea is that each has their own, each of the probes have their own advantages. Weak lensing obviously sends it directly to dark matter, so that's a good thing, but typically it's just a 2-dimensional projection. So it has large sampling variance, especially in large scales. On the other hand, galaxy clustering, we can measure the redshifts, we can do, in principle, a three-dimensional analysis, and so we have many more modes. But then we have to relate galaxy clustering to the dark matter clustering. That's the issue of bias that I talked about. But I also told you how we can solve this issue of bias by doing these cross correlations. Now, what about the fact that can we use this information that we have so many more modes in galaxy clustering, combine it with lensing to reduce the sampling variance? And the answer is, in principle, yes. This was the idea that Willy Penn proposed, that basically if you have this projection of lensing, which is some weighted projection of the density along the line of sight, you can combine the galaxies using the same window, projected window. And then if you take the ratio of these two, the density perturbation itself will cancel. Sampling variance or cosmic variance, where does it come from? It comes from the stochastic nature of the density fluctuations, right?